And that's where we get the nice parabola, hyperbola. So this guy's going to be, so if I want to draw it, I don't know if I want to draw on the same one, but if I want to draw it on the same one, this would be on the x-axis like we said earlier. Like one away, and then shoot. Shoot. So that's stepping away from the xc plane, out along the y-axis. All right, I like it. And if I step the other direction, same thing's going to happen. Just now it's going to happen if I let y equal -1. That is going to turn these bad boys around. Divide by negative. And now I got a hyperbola back the other way sitting like this. And it's going to extend in both directions. And as I move away from the xc plane, what's going to happen to these? They're going to move further away. And then they're going to move further away. So this would be for k equal to 1. If I let k equal to -1, now I'm here. So again, if you want to, this might not be a bad idea to do it in different colors. Try to get some color pencils. And you can do like the further away stuff darker and the closer stuff lighter, possibly. So you can kind of read this easier. It's hard to think of this. I'm basically capturing 3 dimensions, but I put them all as if they're shadows in 2 dimensions. So that's what a trace really is what would it look like if I just was able to just come in and here's a circle and I'm just going to push it into 2 dimensions. And that's what it would look like. I just flattened it, right? Just fell on it. Cool, so if I let k equal to 4, k equal to whatever, it's going to be the same thing, just further away, and now it's moved out some. So it's going to do like this, away from the xc plane. So if you look at, here's the xc plane, and I've got that and that behind it. And on this side, so let me see if I can get this. So behind it, you freeze. Stay right there. Okay. So behind it, it's supposed to be up here and down there. In front of it, it's supposed to be like this. All right. So behind it, sure enough, it's up here and down there. In front of the plane itself, it's supposed to be along the x-axis, and it's well, let's see. So it's definitely like this over there, and in front of it, it's supposed to be like this, and moving away, it's supposed to get further out. And that's the part that's not the easiest to tell, but it certainly has. Let's see. I don't want to say. Oh, yeah. That's the part that's not easy to see on that thing. But you can certainly eliminate all of the other ones, basically. Right? But at least this part you guys can see. As I move further back, these hyperbolas get further away. The reason this is hard is because they've given me this hard edge here. They should have given me some more traces to go by. They didn't, that's when they drew these, they didn't give enough internal traces. So what you have to do is you have to do enough traces until you can see a trace that's actually shown on this picture. So that's what threw me off, is they didn't give enough. See this line here? That's beautiful. That's helpful. That matches up with what I expect. They didn't give me any traces on this side that matches with what they would be. Yeah. Exactly, yes. Cool. You could also, I think somebody might have said this, you can also look at the equations and match them up with these. I mean, this is part of the reason why they give us this, so you know what to expect them to look like. Right, so the one we're looking at right now is y equals x squared minus z squared. Which one does that match up with? Does it match up with any of these? And again, remembering that the variables themselves are dummy variables. I can have z be x, be y, it doesn't matter. So which one has us? One of the variables is degree 1, and the other two are degree 2, with a minus sign in between. Are there any that look like that? Not on the page, but oh well. Contort my book. This one. This is that saddle point that I was talking about, and this is the way they should have given that picture. This shows all of the nice, it's not the easiest to see still, but at least you can see some of the traces in there. So yeah, exactly. So now ours is going to be, so this one you can see the Z axis for ours is now, if I remember correctly, the Y axis, yeah. So whatever this one does along the Z axis, ours is going to do along the Y axis, and so forth. So that's the other half of this, which would have been nice if I would have thought that in the first place. You're not totally on your own with these. You've got that whole chart to kind of look back at and tell what it is, what shape it should be. So you're not in the dark. Okay. So for any of those, this whole section, you could certainly take it back and see what it should look like. Right? And what I'm going to want from you on the test is I'm going to ask you to do some traces and then explain to me what it should do as you move away from the plane, and then I haven't figured out exactly. I'm not going to make you draw the thing yourself. That gets a little hard. But I might make you try to identify which one it is. And I'll give you more information. I can have computer-generated stuff, thank God, that actually gives you internal traces to make it a little easier to see. Yeah?
So it'll sort of be like 20. You won't have to draw it. You'll give us options.
Yeah, and the thing that's missing from this, that would have made it a lot easier to see, is that they have this here, but they don't have anything on this side. And they make it stop at like this hard-edged, and that's a very misleading kind of thing. So I agree that's a weird question. But the other side of this is you eliminate everything else, basically. Process of elimination, it must be this dude. Right? None of the other things do what I need it to do.
But we won't have to draw it.
No. I will make you draw a little something, but not something quite that intricate. Right? Okay. All right. Let me get into 13 just a little bit, because 13 is just so nice to start off with. You like how I said that? And then we get kind of freaky. But if I ask you, what do you hope this would be? It's a weird question to ask you. I'm not saying let's make this whatever we want it to be. But if I asked you this question, if I gave you R of t, what do you got, Jeff? I don't know, Jeff. The beautiful thing about vectors is so much of what we do is component by component. Not everything that we do is, but so much of what we do is. If I scale or multiply a vector, I just take each component and multiply it by that scalar. If I subtract two vectors, I just subtract the equivalent components within the vectors, right? So taking the limit, I can just pull it in. As long as those limits exist, then I can figure out the limit of this vector function, right? So if I do pull this limit in, what do I get? 1. 1. I like it. So does this exist? Does that limit exist?
No.
No. Good. I love it. So it's just that easy. So sure enough, this one does not exist. Specifically, one component goes to negative infinity. But there is no limit for this. There's some kind of asymptotic behavior there somehow, right? We're not going to get that deep into it yet. But thank God is exactly what you would hope would happen. The limit of a vector is just the limit of the components. Each component by itself. It's beautiful. Sometimes it won't exist, but otherwise it's just as easy as long as you do it correctly. The limit is just that easy. That's awesome. Which means, when you took Calc 1, what'd you do right after you finally figured out all the limit stuff? What'd you get right into after that? Derivatives. I love it. So since the limits act on each component, then the derivative will also do that. So what would you think that is? Well, it's the limit as h goes to 0 of r of t minus r of t naught, or even just t plus. Let me put that in the right place. There you go. over h, which looks disgusting. But remember, I can replace this with all its components, and then I can attack each component of it, right? So if I say that r of t is f of t, g of t, h of t, then r prime would involve this, pull that limit inside, then this would just become, of course, f prime by definition, g prime, h prime. Crazy. Okay. This is exactly how you would hope, and it's just because of the way that the computations required to do a derivative are simple to do on vectors, because they deal with components. It's taking the difference between two, is taking the difference between two components. All right, how are we doing there? I mean, that's really all. So section 13.1 is all about, they start off with the limits. Make sure I don't miss anybody here. Yeah, actually, yeah, I thought they did more. 13.2 does derivatives and integrals. So what do you hope happens with integrals? You hope they are not here, but they're here. They're there. Make sure I get everything. Oh, okay. Cool. So that's too awesome to believe. I mean, that's beautiful. So let me ask you this. If I had this, this example I want to use. There we go. Start with this so you can see what this idea is. This is kind of nice. Let's take us back a little bit. If I took this guy's derivative, it's almost too easy because every component, what can you tell me about the functions that are the components of this vector? They're all really nice because they're all linear, truly linear, right? So r prime is just going to be -1, 2, 6. Now somebody give me a better, what is that symbol used for this? If I look at this as it's a line, because really, I mean, I should have asked this, what is this? Why is that the definition of a line? If I break it up, let me ask you, if I break this up, take all the non-t stuff out, what do I get? And then I'm going to add it to t times -1, 2, 6. That's the direction vector, right? And it makes sense. If I took the derivative of something whose direction is constant, and like, not constant, but it's just going in the same direction always, then the answer should be that. Again, this is my m. I like it. So it's only when this stuff inside becomes e to the t or ln t or t squared, then my result's going to be some actual, truly function answer. Okay, I like it. How are we doing there? It's nice to see something familiar. Yes?
So, what if that was a plane?
So what would it look like?
Yeah.
All right.
Get the derivative of plane.
Well, first off, can you give it to me in this form?
I guess probably not.
So it's got to be, one reason you can't do it is because a plane is a collection of an infinite number of vectors, right? And they're all in different directions. So there's no singular way to capture them like that, right? Oh, it's about time. Shit. So we're going to go up through 13.2. So don't worry about number 7 on the practice test.
You want us to have that done by Wednesday?
No. Homework is due by Monday to not be late. So you have until Monday to finish through 13.2. This practice test, you don't have to do it all if you don't want to. I'm going to have the answer key on Monday. Yeah, so don't turn this into me.
Wait.
Sorry, Wednesday. Sorry.
So you said we don't have to worry about number 7 on here?
Number 7, no, that's from 13.3. We didn't quite do enough for that yet.
So I had a question about the correction for the homework.